does this infinite sum involve pi over 6? Okay, so let's get straight into it. So first of all, I'm going to write this in sigma notation. Now, if you don't know sigma notation, it's just equivalent to writing out all these terms with dot dot dot. It's just a more compact way of writing it. So we write it as sigma, and it's an infinite sum, and we're going to start from n equals 0, and we have minus 1 because it's alternating to the n. Well, we're divided by the odd numbers, so it's going to be over 2n plus 1, and then it's 1 over cube root of 3 raised to that odd power. This is the same as this. Now, zoom out and take a look. So maybe we could try and use geometric, sum to infinity of a geometric. Not quite, because it involves this term here, which is not very nice. However, if you stare at it long enough, okay, what do you see? I mean, we see that the power here and the power here is the same. Sorry, the power is the same as what we're dividing by, okay? What does that remind us of? Well, that's the same thing as doing integration, right? So maybe that might help. But, you know, this doesn't involve a variable, this is fixed. So I guess we could say that this part, we could say that this is equivalent to writing the sum from infinity, n equals 0, the minus 1 stays out, but this bit, well, this is going to be the integral. It looks like the integral of x to the 2n, because remember I've raised that power, so it'd be x to the 2n plus 1, and then I divide by 2n plus 1, with respect to x, obviously. But then when I do that, I want to get 1 over the cube root of 3, right? So my bottom limit's got to be 0, so vanish that away, and the top limit's got to be cube root of 3, okay? Perfect. So now, with this, well, we know what we can do with integrals, right? We can bring the integral sign out. And if you don't believe that, just write out a few of these terms, and you'll see for yourself, we can definitely bring the integral sign out. So we bring the integral out of the front, and we switch places. And now we write, so we bring the integral sign out to the front, and now we switch, okay? So it's minus 1 to the n times x to the 2n, okay? So if you don't believe that, just write out a few terms. Wow, 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 this is looking more promising. Okay, so we have the sum to infinity of this. Well, it'd be nice to combine this, and then maybe we can use geometric. So if we combine this, well, it's got the power of n, common in both, so I can just rewrite this as the integral 1 over cube root of 3. 0 is my bottom limit, as it was before. Sum to infinity, n equals 0. And then I'm just going to combine this, it's minus 1. X squared to the n. So when I times it out, I get minus 1 to the n. And then I get x squared to the n, which is x to the 2n. Perfect. Well, now that's an infinite sum of something where it's just timesing by minus x squared each time. Okay, so that's an infinite geometric series. So I'm just going to come up here. So we've got the integral from 1 over cube root of 3, 0. Well, this is geometric. So I can just apply the formula. Remember, the formula is a over 1 minus r, where a is the first term in your sequence, and r is the common ratio that you times by each time. So let's just get that down. So that's going to be, well, a is when I put n equals 0 in here, so that's going to give me 1, over 1 minus r. Well, r is this bit here. So it's minus x squared. Okay? Well, now we see here, right? We see here, look at that. Boom, those two minuses, it was minus minus, so that's going to become a plus. Right? And now that's looking very, very promising. That's looking very promising. Now we're just left, we have this entire thing, we've brought the integral sign out, we've used geometric series, and now we just get an integral. Well, this is just the integral of tan x. So, sorry, arc tan of x. So this is going to be arc tan of x. The limits being 1 over cube root of 3, 0. Arctan of 1 over cube root of 3 equals pi of 6. Arctan of 0 is 0. So this is equal to pi over 6.